Welcome back to AI.Code.Cast, everyone. Ready for another deep dive.
Definitely. Always excited to tackle some cool coding challenges.
Today we're taking on combination sum IV.
Ooh, that's a classic. It's a favorite in those technical interviews. You know the ones.
Yeah, it's a real brain teaser, isn't
For
it?
sure, it makes you think about efficiency and algorithms.
So let's break it down. Imagine we've got a set of numbers, say 1, 2, 3, and our target is 4.
Okay, I'm following.
The goal is to find how many different ways we can add those numbers to hit 4. But there's a twist.
A twist. I love twists. What is it?
Order matters in this one. So 1, 2 is different from 2, 1, even though they add up to the same thing.
Ah, I see. So it's not just about picking the right numbers, but also the sequence. That does make it trickier.
What makes this problem stand out, and why do you think it's such a hit in interviews?
Well, combination sum of E really forces you to think about how to solve problems efficiently. I mean, you could go the brute force route, try every single combination possible, right? But as the set of numbers and the target sum grow, that method just gets way too slow.
It's like trying every single key on a giant key ring until you find the one that unlocks the door.
Yeah, exactly. There's got to be a smarter way.
There has to be. So what's the secret weapon here?
Dynamic programming. It's all about breaking the problem down into smaller, more manageable subproblems, and you store the solutions, so you don't have to redo all that work over and over.
So we're strategically mapping out the best route to our target sum, using the solutions to smaller sums along the way.
Precisely.
Love it. Now, in dynamic programming, aren't there usually multiple paths to the summit? What are the main approaches we can take for this particular problem?
You're right, there often are. For combination sum 4, we have two primary strategies. Top-down, using recursion and memoization.
Okay, I've heard of memoization. It's like taking notes so you don't repeat calculations, right?
Exactly. And then there's bottom-up, which uses an iterative approach, building a table of solutions as you go.
So two sides of the same coin, both aiming for that efficiency we're after.
Exactly.
Before we get into those specific approaches, can we maybe try cracking this problem with the brute force method first, just to see what we're up against?
Sure, let's do it. Let's use our example set of numbers, 1, 2, 3, and target sum of 4. Brute force, we'd start by trying all combinations of length 1, then 2, and so on. A lot of checking and recalculating.
And I can already see how that would get out of hand fast as the numbers get bigger.
Oh, absolutely. Brute force might work for these tiny examples, but it's not going to cut it for larger problems. That's where dynamic programming steps in.
Okay, so let's ditch the brute force and start climbing smarter. Let's start with the top-down approach. I'm thinking of a climber rappelling down from the top of a mountain, strategically placing anchors along the way.
I like that visual. So in the top-down approach, we're talking recursion. It's like defining a function that keeps calling itself to solve those smaller pieces of the problem.
Okay, so we've got this function. Let's call it combination sum 4. It takes our set of numbers and the target sum as input. Then what?
Well, hold on. Before those recursive calls, we've got to handle the base cases, those simplest scenarios where the answer is already obvious.
Right, got to start somewhere. So what if our target sum is 0?
Then, boom, we don't need a numbers from our set to hit the target. We're already there. So we'd return a count of one valid combination.
Makes sense. And if our target sum is negative,
Uh-oh, we've overshot the target. No way to recover using only a positive numbers. So we return 0, no valid combinations.
got it. Those are our base cases, our starting points. Now what happens next? How do we use the numbers in our set?
All right, here's where it gets interesting. For each number in our set, we check if it's less than or equal to our target sum. If it is, we might be able to use it right.
Like checking if a brick fits into our tower before we try to place it.
Exactly. If that number fits, we make a recursive call to our function, combination sum 4, but this time we subtract that number from the target sum.
Ah, I see. We're saying, okay, let's say we use this number. Now, how many ways can we reach what's left?
You got it. And we do this for every number in the set that fits our criteria.
So we're breaking the problem down. But are we going to end up repeating a lot of calculations if we keep calling the function with the same inputs?
You're sharp. And you're right, we could. That's where memoization comes in. It's like taking notes as we go along so we don't have to solve the same thing multiple times.
Like a web browser caching websites so they load faster.
Exactly. We use a dictionary or hash map to store those results. If we run into the same target sum again, we just grab the answer from our memoization table. No need to redo all that work.
Super efficient. But are there any downsides to this memoization magic?
Well, you got to keep in mind that recursion, even with memoization, could lead to a stack overflow. especially if you have a huge target sum or you go really deep with the recursive calls.
So it's powerful, but you got to use it wisely.
Right. So that's top-down, elegant, intuitive, but watch out for those stack overflows. Now, what about bottom-up? How does that work?
Yeah, let's explore that. I'm ready to switch gears.
Great. Remember how we talked about building a table where each cell represents a possible sum?
Yes, like we're constructing a solution, brick by brick, level by level.
Exactly. That table is our memoization, and we fill it up very systematically.
Okay, I'm intrigued. Tell me more about this bottom-up approach.
All right, so we start with our table, which is usually called DP. This DP array has target plus 1 elements, all set to 0 initially. Each element's index will represent a possible sum, and the value stored there is the number of combinations for that sum.
So DP0 would be the number of combinations for a sum of 0, DP1 for a sum of 1, and so on. Very visually clear.
Exactly, very structured. Now, there's only one way to get a sum of 0, using no numbers. So DP0 starts at 1.
Got it. That's our base case for this approach. What about the rest of the table? How do we fill it in?
Here's the magic of bottom-up. We use 2 nested loops. The outer one goes through every possible sum from 1 up to our target.
Okay, so we're taking it one sum at a time.
Right. The inner loop goes through each number in our set.
So for each possible sum, we check all the numbers that might be part of it.
Yeah. Now, inside these loops, first thing we do is see if the current number is less than or equal to our current sum. If it's too big, we skip it.
Right. Got to make sure it fits into the sum.
If it fits, we update the DP table. We add the value at DP num to the value at DP, where I is our current sum and num is the number we're looking at.
So we're looking back at the table at the index representing some number.
Exactly. That DP num already holds the number of combinations for that smaller sum. By adding it to DPi, we're saying we can reach the current sum by using this number plus all the combinations we already have for the smaller sum.
So we're building upon what we've already figured out. I'm starting to see how this bottom-up approach works.
It's super systematic and efficient. And once that outer loop is done, the last cell in our table, DP target, will have our answer, the total number of combinations to reach our target sum.
So elegant. Just return DP target, and we're done.
Pretty much. It might take a bit to wrap your head around the logic at first, but it's really beautiful in action.
I agree. Now, I know we've only scratched the surface here. Are there any common gotchas we should watch out for with combination sum IV?
Good question. One thing is integer overflow. If the target sum or the number of combinations is huge, we might exceed what our data type can handle.
Our solution could break just because the numbers get too big.
Potentially. That's why you might need larger data types like long int in C++ or long in Java, or use modular arithmetic if all you need is the remainder after dividing.
Like safety nets, just in case things get a little crazy.
Exactly. Another thing to consider is negative numbers in the input set.
Oh, right. What happens if we have those?
Well, our examples have been using positive numbers. If we allow negative numbers without any rules, you could have an infinite number of combinations. Just keep adding a positive and negative number over and over again.
We'd get stuck in a loop forever.
To fix that, you'd need to add some constraints, like limiting how many times you can use a negative number, or setting a minimum for the total sum.
So we're adding rules to keep things from going haywire.
Exactly. We want our code to be solid, no matter what kind of input it gets.
Well, this has been a great start to our deep dive. We've explored the problem, tried the brute force approach, and gotten a taste of both top-down and bottom-up dynamic programming.
We've covered a lot of ground for sure.
And learned about those potential pitfalls like integer overflow and the whole negative numbers thing.
Making our solutions stronger and more reliable.
I can't wait to dive even deeper into those dynamic programming approaches, especially to see how we actually turn these concepts into code. Ready to walk us through some pseudocode examples?
Absolutely. Let's break it down step by step. Let's start by visualizing that top-down approach, with the recursive calls and memoization.
Perfect. I love how recursion is like exploring a branching tree of possibilities. You make decisions at each step.
It really is. So imagine our function, combination sum 4. It takes our list of numbers, nums, and the target sum as input.
Okay, got it. Those are our ingredients.
Inside the function, we create a dictionary. Let's call it memo. This is our memoization table, right? It's going to store those results so we can look them up later.
Makes sense. Like a cheat sheet for our recursion adventure.
Exactly. Now, the first thing we do, always, is check those base cases. If the target sum is 0, we've got one valid combination, so we return 1.
Right. Because not using any numbers is a valid way to get to 0.
And then we check if target is negative. If it is, no valid combinations. We return 0. We've overshot.
Got it. Always going to handle those edge cases first.
Now, before we jump into recursion, we check our memo table. If the target sum is already in there, we've already calculated the answer for this subproblem.
Smart. So we just return that stored value, skipping a ton of work.
Exactly. Now, if target is not in memo, it's a new subproblem. So we start a counter, let's call it count, and set it to 0. This will keep track of the combinations for this target.
Okay, count starts at 0, and we'll add to it as we find those combinations.
Now, we loop through each number, num, in our list nums. For each num, we check if it's less than or equal to our target sum.
If it's bigger, it can't be part of the solution, right? Got to fit within the target.
Right. If it's less than or equal, we make that recursive call to combination sum 4, but we pass in target num as the new target.
We're basically saying, if we use this number, how many combinations can we get with what's left over?
You got it. And we add the result of this recursive call to our count.
So count keeps growing as we explore those subproblems.
Once we've gone through all the numbers in nums, our count will have the total number of combinations for that original target we started with.
Okay, so what's the last step? We've explored everything, right?
Almost. Before returning count, we store it in our memo dictionary. That way, if we see this target again, we have the answer ready to go.
Always learning and remembering.
And finally, we return count. That's the total number of combinations.
The top-down approach in action. It's amazing how we can break it down and make it so manageable with recursion and memoization.
Recursion is super powerful when you use it right.
Now, I'm really curious about that bottom-up approach, the one where we build the table.
Let's do it. Remember, each cell in our table, DP, represents a possible sum, right? And it stores the number of combinations.
Yeah, like a grid where we fill in the values systematically.
Exactly. So for our bottom-up pseudocode, the function combination sum 4, it still takes the same input, nums, and target.
Same inputs, different strategy.
First step, we create our DP table. It's a list or an array with target plus 1 elements, all set to 0 at the start.
Okay, so the table size depends on the target. We're setting up for all the possible sums from 0 up to our target.
Now, our base case, remember, only one way to get a sum of 0. Use no numbers. So DP0 is set to 1.
Right, that's our foundation, the starting point for building up our solution.
Now comes the fun part. 2 nested loops. The outer loop, it goes through every possible sum I from 1 to target.
Okay, we're going one sum at a time.
The inner loop goes through each number, num in our list, nums.
So for every sum, we're looking at all the numbers that could be part of it?
Inside the loops, first we check if the number num is less than or equal to our current sum, I. If it's bigger, we can skip it.
Got it. Gotta make sure it fits.
If it fits, we update DP. We add the value at DP num to the value at DP I.
Hold on. We're looking back at the table at the index that represents some number.
Yep. That DP num already has the count for that smaller sum. By adding it to DP, we're basically saying to reach the sum I, we can use num plus all the combinations we already have for inum.
It's like we're using what we already know to solve the bigger problem.
Exactly. And once that outer loop finishes, DP target will have our final answer, the total combinations for our target sum.
So we just return DP target and that's it.
Pretty much. Elegant, right?
Really elegant. It's amazing how much is packed into that.
The power of dynamic programming.
I'm really starting to see that.
Yeah.
So we can go top down with recursion and memoization, or bottom up, building the table. Both get us to that efficient solution.
Exactly. It often comes down to personal preference, you know, what feels more natural to you.
It's like having different tools and choosing the right one for the job.
Now, before we wrap up combination sum IV completely, any other questions about these approaches? Anything else you want to dig into?
I think we've got the main ideas down, but maybe a quick recap, just to highlight the key takeaways for our listeners.
Sounds good to me. So what are the essentials to remember when you encounter combination sum IV out there in the real world?
Well, first we learned that brute force, while it seems simple, just doesn't scale well.
Yeah, it's tempting to try every combination, but it gets really slow, really fast.
So we need something more powerful.
Dynamic programming.
And we saw 2 great ways to do it. Top-down with recursion and memoization, and bottom-up, where we build that table of solutions.
Both approaches take advantage of breaking the problem into those smaller chunks, those subproblems, and they both save us time by storing and reusing the answers to those subproblems.
It's like a team effort, everyone working together to reach the solution.
Exactly. And those base cases, remember, super important. They're our starting point.
Right, like the foundation of our solution.
Now, even with dynamic programming, we got to watch out for those gotchas. Integer overflow if the numbers get too big.
Got to be prepared for that.
Choosing the right data types or using modular arithmetic can really help. And then there's the whole thing with negative numbers in the input.
Yeah, that could really mess things up.
Adding some constraints can keep things under control.
So it's not just about applying the algorithm blindly. We need to think about the details, the edge cases, and have a plan.
Couldn't have said it better myself. Combination sum the veal is a great problem to practice those skills. It helps you become a better problem solver overall.
It's like a workout for your brain. Now, before we wrap up completely, I have a thought.
Go for it.
We've been focusing on counting how many combinations there are. What if we actually wanted to list all the valid combinations?
Interesting twist. That does add another layer of complexity, doesn't it?
It's like not just finding the number of paths, but actually drawing out each path on a map.
Exactly. You'd need to tweak the approach a bit to do that.
Maybe something for our listeners to ponder.
I like it. A challenge for everyone to try. It's a great way to really master these concepts.
Well, I think this has been a fantastic deep dive into combination sum 5. We've gone from brute force to the elegance of dynamic programming, explored different approaches, tackled those potential pitfalls.
All while keeping things clear and engaging for our listeners. I hope they're feeling inspired.
Me too. To everyone tuning in, remember, dynamic programming is a powerful tool. Don't be afraid to experiment, try different things. The more you practice, the better you'll get at solving all sorts of coding challenges.
That's all about learning and growing.
Exactly. Thanks for joining us on this deep dive. Until next time, happy coding, everyone.
Happy coding!